that'll be very, very interesting. We're actually really looking forward to the update. Then next week, it's amazing, it's May, practical machine learning for COVID-19 using EHR data, case study using N3C by Brad Price and Miriam Kodarvti, sorry, I'm bad at pronouncing names. Phenotype 4.0 by Emily and Sean. Then the BARDA challenge updates, May 9th, May 16th, use of cardiopulmonary exercise testing and addressing issues like fatigue and pediatric PASC, Dan Cooper. Then May 23rd, outcomes of COVID-19 in patients with hemophilia, monthly recover long COVID project team updates. I think we're going to try to get an early June or mid-June meeting with Midrick and TPRL imaging. I was just talking to them. We're overdue for an update on that. Okay, but next slide. Without further ado, and we're skipping a week on the dashboard. And we'll have a contest as to who can guess what the numbers are next week. Well, probably we won't. Okay, so Peter.
I think Justin's going to present it today.
Right.
Yep. Figure out the right screen to share here. Can everybody see my screen?
Right. Yeah.
Okay, great. So we talked about our PASC clustering data last week, and I'll present some of that again this week just to sort of frame this. But what we're going to talk about is some insights we think we've gained into good algorithmic practice while we've been fleshing out this long COVID clustering pipeline. And actually, so this is actually cross-cutting work with the Recover clustering team. That's Reese Madlock-Brown, Melissa Handel, Sean O'Neill, Peter, who's obviously, we've actually made another machine learning pipeline to predict AKI and cardiovascular outcomes in COVID-19 patients. Most of our work, though, has been on this long COVID patient clustering data, and so we'll sort of frame it with respect to that pipeline. And as I said, we'll hopefully give you some insights and some maybe some things we've learned along the way with respect to good algorithmic practice in the course of several months of doing this. And specifically, workflows that have worked well to promote good algorithmic practice, and also maybe some even more practical advice about the N3C tooling that we've used for this, and sort of the strategies for using the different tools that are available in the N3C enclave, and then also some organizational strategies and sort of touch on the socio-technological issues. I think that can inform the way that we approach these problems. And I'll also give you some not so preliminary now clustering results on long COVID patients and some analysis of the clinical relevance of those clusters. But again, so the goal here is to make at least the short-term machine learning goal is to make long COVID clusters of long COVID patients using the phenotype data directly, and so it's sort of data-driven clusters of long COVID patients. There are clinicians and biologists who've been studying this for a few years and can probably tell you what different kinds of clusters exist in the data. But the idea here is to let the data tell us what clusters exist, and as I said, analyze them for clinical relevance. And we also have some data to show about generalizability of these clusters. In other words, if you make them in one data center, how well can, how appropriate, how well does it work to cluster patients from different data centers using those same clusters? And we, I think, also have made some reusable code and tools that we'd like to give to the community and show everybody how to use them. But the first problem, if you're going to do this, is to extract and compare phenotype data from N3C data. And that requires some measurement of how similar to long COVID patients are. There was tooling made, I'll get into this in a second, by Tiffany Callahan and Andrew Williams, specifically OMOP to OBO, that allows you to actually extract HPO terms from mostly from the condition era table. And so being that we can do that, we can compare the HPO terms for any two patients. And this is, as I say here, is sort of an operationalization of those OMOP to OBO mappings that Tiffany and Andrew have made available. So to frame the question, how similar are these two patients? So here's patient A, here's patient B. We might have these three OMOP terms for this patient describing their conditions or phenotypes, and these four for patient B. And obviously it's pretty trivial to do exact matching. And then if you did something like OMOP rollups, you might find that respiratory finding is similar to cough, and acute kidney injury is similar to transient renal failure. But there's actually, we think, a better way of doing this, which we've implemented in the enclave, and that is semantic similarity that leverages the HPO graph. So specifically, so in this particular example, acute kidney injury and transient renal failure from patients A's and B's would be mapped to these HPO terms, acute kidney injury and reversible renal failure. We go find their common ancestor, which is, in this case, renal insufficiency, and we calculate the information content of that common ancestor. Information content, for those who aren't familiar with it, is sort of a measure of how meaningful or surprising a match on this term is. And so this takes into account how often you see this term. And so obviously things that are very specific are more meaningful, and things that match like way up on the HPO DAG are not so meaningful. So this gives you kind of a fine-grained way of saying exactly, actually deriving a floating point number that says how similar this OMOP term is to this OMOP term. So we can do that for all the phenotypes for patient A versus B. We find their best match and find their information content and average those. And then do the reverse, patient A versus patient B, and average all of these, and then average that average. And then we have a very, we think, elegant way of saying exactly how similar phenotypically patient A's long COVID phenotypes are to patient B's. And this, by the way, is implemented in, this is implemented in the enclave. Anybody can use this. There's some tooling that goes along with this too that is useful for doing statistical tests on clusters and things like that using semantic similarity. But this is shared across the enclave with this library name. So then to cluster the patients, we use k-means clustering. So specifically, we'll find all the diagnosed UL9.9 patients. We're not using long COVID clinic attendance here. And then for one data partner, we found 1,234 patients. We find all their long COVID HPO terms. This is leveraging work that Peter and Melissa and others did to identify what HPO terms we should be using, we should be looking for in long COVID patients. And then we just generate an n-by-n patient similarity matrix, and then we can feed that right to the k-means clustering algorithm. This, by the way, also is implemented in the enclave. Anybody can use it. And again, there's a lot of tooling that goes along with this to sort of analyze and manipulate these clusters. So everybody's welcome to use it. Here's kind of what the data looks like. This is, in some sense, the space over which we're clustering. This is the first and second principal component of the patient similarity matrix that we're using to cluster on. Here I'm showing you the pairwise similarity patients of that same matrix, but it's organized by clusters. So here's cluster 0, 1, 2, 3, and 4. You can see these off-diagonal signals of how similar cluster 0 is to 1, 2, 3, 4, and so on. So conceptually, this is kind of the space that we're clustering over, and these are the resulting clusters. So to analyze them, you can do a chi-square to figure out, which HPO terms, which again were used to generate the similarity matrix itself, which HPO terms correlate with cluster membership. This is also implemented in that same library. We found 49 long COVID HPO terms that correlate with cluster membership with a p-value less than e-6. Before I show you some data on what those are, we'd like to know how these clusters compare to data from other data partners. In other words, getting at this question of generalizability. If you do that exact same experiment I described previously on 4 different data partners, not the ones that we clustered on, but different ones, we find 44 of those same 57 long COVID HPO terms that are also that correlate with cluster membership. And we can actually use those terms to characterize each cluster. So that's what I'm showing you here. This is with a cluster K of 5, in other words, the 5 different clusters. And I don't expect you to be able to read these rows, but the columns are the clusters, the 5 different clusters, and we've sort of color coded them by the types of the long COVID symptoms. So this blue color is cardiovascular, this is pain, GI symptoms, lab is kind of the catch-all for any abnormal lab value, neuropsychiatric and pulmonary. You can see cluster 0 seems to be the cluster that you don't want to be in here. This is most severe, and you see symptoms that span pretty much every category that I just described. Cluster 1 seems to be more that same picture, only less so. Cluster 2 seems to have frequent neuropsychiatric symptoms. Cluster 3, frequent pain and cardiovascular complications, and cluster 4 seems to involve mostly pulmonary symptoms. So just a bit on next steps. We actually have determined that there's a method called the elbow method, where you can sort of look at how well the data comports with how the patients comport with the cluster that they're in to measure the optimal number of clusters. That seems to be 6. And so we've done all the experiments I've described with 6. This next question is especially interesting to us, the generalizability across data partners. So we've done an experiment. I won't show you data in the interest of time, but to get at this question, we measure the similarity of held out patients from 4 different clusters to existing clusters, and then you'll get some distribution of how well they sort of belong in any one of the clusters. We measure the similarity in random clusters to sort of generate a null model, and then good generalizability means a strong tendency of patients to be similar to one cluster more than you would expect by this null model. The z-scores for this are extremely high. They're about 100, so way higher than you would expect by chance. And this is sort of a hint, we think, that this might be sort of a generalizable model that could be clinically useful. So we're also in parallel examining a lot of other clustering algorithms, spectral clustering, hierarchical clustering, and others I think have presented. Sean O'Neill, for example, topic modeling, and Haitham Sikki has a lot of interesting data on SNOMED-DVEC. And so this is very much one of some parallel efforts to get at this. But I wanted to also share some thoughts about how to design projects to get these sort of things done in the enclave, that sort of gets to the good algorithmic practice facet of all this. We produce several robust Python libraries that are well unit tested, and those are, everybody's free to use them, obviously. We needed for this reproducible transform code to make the cohort and actually produce the similarity matrix. And then obviously we want some visualization that I just showed, and other analysis and sort of code that kind of dives down into the actual data. So the tools that are kind of available for this and kind of decreasing complexity are code repositories. The nice thing about these is you get an IDE, it's an integrated development environment, and a lot of GitHub-like features that most software developers who've done this for a while are very comfortable with. And you get a source control management solution similar to Git, and you get pull requests, and the debugger is especially nice for me, and you get syntax highlighting, and it just makes coding a lot more like what a lot of developers are used to. It generally has better tools for sharing code and provenance, and more convenient. This is more of an environment that developers are used to. Code workbooks are also available. The advantage here is you have support for R. And this is obviously crucial for some use cases involving, for example, propensity matching and epidemiology. better support for visualization. And this tends to be a little bit more convenient for new developers or people that are sort of climbing the learning curve, and also is quicker for prototyping. And Contour is another, I think, sort of often overlooked tool that you can use here for quick hypothesis testing and data exploration. And this is usable for non-software developers too. And so the solution we sort of tend to converge on is to kind of go as high on this list as the logistics or the people involved or the solution, the actual specification allows. The typical workflow that we've used in our group, which I wanted to share, is to do data exploration in Contour, kind of as a group, design and implement to take a hard look at what reusable code you're going to need to make, and design and implement that code as a shared Python library, if that's possible. That requires you using a code repository. Writing the transform code as also as a code repository, and then doing the analysis and visualization in a code workbook. Some thoughts. I think I have 20 minutes. Is that right? How am I doing on time?
Yeah, no, you're doing great.
Okay, good. I wanted to also share some thoughts about sort of the takeaways and lessons we've learned doing all this. Is yeah, like I think I said this before, that an effective workflow is data exploration, implement the reusable code as much as possible, use that to do Python transforms, and then use a code workbook for visualization stuff. Another thing that has worked well for us is frequent participatory team programming. So pair programming, but with 5 people, or as many people as who you can muster who are interested. And this tends to give you better code and quicker debugging. So the saying is, given enough eyeballs, all bugs are shallow. We definitely have found that to be true. And also to really look for opportunities for code reuse. It's sort of easy to deceive yourself when you first start writing code that you're only going to write it once, and there's no point in writing reusable code, but that's often not true. It's often there's a lot more reusable code in hiding in a project that you can sort of extract out. Testing is, I'm a big proponent of test-driven development. Frequent, or at least one code review before you go public with data, and as I said before, team programming is very useful for us. Obviously, being inclusive and having a collaborative team, like you want as many people involved in the effort as you can reasonably manage. And also, I think we have a great community here, and so if you have some sort of kind of esoteric problem that you're stuck on, you can always ping the community, and this has helped us a lot in unblocking ourselves. And so just find out who can help you, and without exception, when we track people down, they're always very willing to help, and vice versa. We're always willing to help if people ping us and want our opinion about something that they're blocked on. I just wanted to acknowledge all the people who went into producing all the data that I just showed. It definitely was not just me. It was we have frequent, basically daily hackathons, the coffee hackathons. These are our frequent attendants. Sorry if I left anybody off, but I think these are our most frequent attendees. And then all the people who you all know who have contributed in various ways or involved in the MLP working group, and colleagues that have been really helpful in getting all this done. And glad to take any questions.
So this is Chris. I have a question. And Peter, are you going to talk about, are you giving a second talk about the most informative common ancestor issue, or is this the talk?
We're open for questions.
Okay, fair enough. Thanks. This is very elegant. I'm remarkably impressed. One of the things that occurred to me, having dealt with a number of disease hierarchies in the past, is that how rich that hierarchy is in terms of granularity and detail is a function of how well curated it is. and that some pathways, if you will be better curated than others. HPO was clearly targeted or initially focused on rare diseases, and thus the most common informative ancestor is going to be most rich when you're comparing rare diseases. I don't know, and this is a question maybe for you, Peter, for common diseases, how distorted or biased or potentially malleable might this notion of the most informative common ancestor be for less well curated common diseases in HPO, which would impact the information content metric that you generate as that common ancestor?
That's a great question. So without getting into too much detail, the way that we've used information content for rare disease has mainly been to calculate the information content over a set of diseases, and then use that to evaluate queries, diagnostic queries. In this project, we're doing something different. We're not looking at diseases at all. We're looking at patients. And so to calculate the information content, we took the frequency amongst all of the patients in this data set, calculated the information content of each term with that, and used that for clustering. And so that basically tells us within this group of patients, how specific is any one sign? And the actual numbers are likely to be different here than they are for the rare disease. But I would, and obviously nothing is perfect in this world, certainly not HPO, but HPO has been through quite a number of people, and so the hierarchy is at least reasonable, and it should work essentially just as well for common disease as for rare disease.
Fair enough, and that's what I more or less assumed, but I'm just trying to give you a hard time. And then the second question is, it's probable that in PASC that we have temporal effects. That is, PASC after the initial alpha variant versus the delta variant versus the Omicron variant may be a slightly different disease for lots of complex reasons, some of them biological, others having to do with pre-vaccination. I mean, you know the drill. To what extent in this effort do you think temporal manifestations impact your clustering, particularly when you're looking at different? I know you've shown at least better than random chance, better than stronger associations to your discovered clusters in the first site than to random clusters. I get that, but to what extent do you think temporal variation of what PASC looks like over time would impact these clusters?
A lot, and the similarity metric that we used this time is simplistic, so it treats the terms, and all of the terms, by the way, reflect data at least 22 days after the onset of acute COVID. But with that said, we're treating everything that comes after that as an unordered set, and that's because this algorithm is still simplistic. I think there are many different ways that one could try to take the temporal aspects into account. One would be to look at individual patients and see, is the distribution of terms in months, 2 to 3 different from months 4 to 5, and that's something that we're in the process of doing right now. And another thing that one could do, probably not with UO9.9 because it's so recently introduced, but we could go back and try to figure out what people had. That requires a lot more assumptions or machine learning because we can't actually observe which variant patients had from the N3C data. And so I think for now, and Justin, correct me if I'm wrong, but I think for now we regard that analysis as just too hard for what we think we can do.
Well, it's a secular association, really. I mean, we know when the waves were, and so to the extent that you hit the wave, so to speak, you get an approximation of the variant.
Yeah, we've been, I think, one of the next steps that we've been talking about on the clustering group too is, and there's some preliminary work that Sean O'Neill has led with patient epochs, if you will, which are the different kind of phases of progression. So pre-acute phase, diagnosis, the near term post-acute phase, and the longer term acute phase. And you could divide it up into a number of different things. But one of the interesting things I think is we really have to look at long COVID in a longitudinal trajectory sort of way. And I think one of the neat things about what Sean had done is just look at how patients change clusters over time. And so I think in terms of some of the next steps for how we want to validate these clusters, we have to look at it through that longitudinal lens to see if that makes clinical sense in terms of the clusters that exist in those different phases versus how patients, cluster longitudinally with one another. So for example, let's say we have, 3 different, clusters, or the 6 different clusters we looked at today. How do patients change in terms of being included or excluded from those clusters over time, and how many patients are making those same changes in clustering over time as a cluster? So it's sort of like a longitudinal clustering of the clusters, if you will.
Oh, that's fantastic, because obviously PASC and long COVID is an overly simplistic concept. So you have a sort of progression, which it seems like this is a really good way of capturing. Cool. Other questions? So Peter, what do you see as the potential role of NLP methods, in particular, some of the the newer transformer, BERT, GPT-3 sorts of methods in looking at characteristic manifestations of PASC?
Especially for anything related to HPO, a lot of the features that HPO covers are not well covered in the structured part of the EHR. And so it'd be very interesting to use various NLP tools for that. We're actually just finishing a project where we've adapted the BLAST algorithm that people kind of use for DNA or protein sequence.
Yeah, no, I remember that well from back in the day. Yeah.
Yeah, so we have something like that now for text mining that does a really good job with spelling errors and other things like, for instance, microcephaly is an HPO term, but microcephalic is not mentioned as a synonym, but it probably should be. And we could add microcephalic, but actually there are so many things like that it would not be easily doable to just kind of add every possible synonym. But with this tool, we're actually getting, we've evaluated this over Wikipedia and about 2 million Australian records, and we have a pretty good sensitivity and a very low false positive rate.
No, I like that. That's really.
So we'd love to. It's I don't know what the how easy it's going to be to access notes in N3C, but I think our algorithm might be competitive, and certainly we'd love to test it. I mean, maybe it's not, but we'd love to test it. But with whatever algorithm one uses, yeah, definitely, I think I'd like to think that a next step for, at least for anybody interested in HPO and EHR, is kind of hooking up text mining methods to notes and radiology reports and pathology reports. And I think I'm currently trying to get my head around things like this Argonaut implementation guide of FHIR. I think something, if we could work with centers to implement things like that, I think it would open up a lot of really interesting possibilities. And I think connecting this also with the phenopacket format would allow us to essentially develop a library of software for looking at rich representations of phenotypes and their time course of individual case reports. So yeah, definitely, I think this is a really interesting topic and something that we were hoping to follow up.
That's cool. Yeah, no, we've captured essentially the whole pandemic's worth of clinical notes, and are looking at BERT and some of the other methods. So we should chat. I mean, that's
Happy to share a code. Yeah, I'd love to. I mean, even if you just try it out for a brief, it should.
Yeah, no, absolutely love to.
Yeah.
And the other thing is that that federated learning obviously is a thing, and we're working with the Penn group. They've got a system they've developed with Intel. I mean, there are a number of systems out there, and obviously sharing notes is not a real rapid process due to the need to de-identify. So having a bunch of sites do federated training, it's still, I understand, requires agreements because of course the model learns all sorts of things you don't want it to. So the model still has to be locked away. But I think from the standpoint of IRB agreements, if everybody promises to be a good citizen and everything is kept secure, I think a federated approach would be and I agree. I think it's an HPO. It's a sort of phenotype sort of thing, because you're with a lot of these methods, you're not trying to find particular words, you're trying to find broader concepts.
Yeah.
So cool. Okay. Anyway, other thoughts? There are some questions about common ancestors. It looks as though that was answered, but Justin, do you want to address that?
Yeah, if I understand the question correctly, maybe I misunderstood, but so if you have two terms you're trying to compare, you find the most specific ancestor that they have, which is we have tooling to do that, and then you take the information content of that. You could go the whole way up to the top, obviously, but if you go up to the top, then you're going to have an information content of 0. So use the one that's most informative.
Mm-hmm. And there's a question about common diseases in HPO. And I kind of wondered that myself, because I mean, HPO seems like a very cool thing. But obviously the focus of development, as I understand it, has been more on rare diseases. And there was sort of an interesting question of benchmarking HPO for sort of nuanced phenotypes of common diseases, presumably with the notion that not that HPO is a great thing, but there's the issue of perhaps it needs some elaboration in those cases. So do either of you have anything, any thoughts about that? Or maybe it's already been done. I have no idea.
So yeah, I mean, the ontology itself is ready to go, and I think it covers the vast majority of interesting features found in rare as well as in common disease. But the difference is that for rare disease, we also have a database now of 8,500 rare diseases with pretty good annotations for most of them. And we do not have that database for common disease. So that means essentially that we do not have a differential diagnostic tool for common disease in the way that we offer one for rare disease. That said, for clustering like we saw now and other things like that, HPO works. And moving forward, I think we're going to be doing more work with EHR data and at least a selection of common diseases.
Mm-hmm. Cool. Right. Any other thoughts, comments, questions?
I do. I have a tough question I need help on that I was asked today. They said, so there's a lot of folks who are looking to find long COVID patients for recruitment. And what would it take for you all to feel comfortable using things like this we wouldn't be able to identify patients, we would go through our honest broker. But for the honest broker to be using this other than the ICD-10 code for long COVID for recruiting. And it's a tough one, how do we validate this enough that we're comfortable that this is a group we're talking to?
So I think, we've been talking about this a lot. I do think we're getting to the point now where our computable phenotyping with our machine learning classifier for long COVID, as well as the subtyping that was presented here, and there are a couple other methods as well, that together can kind of be corroborating those different, sub cohorts, if you will. There's definitely, I think, the hypothesis that there are subtypes of long COVID, and if we want to have effective study designs, we need to identify those subtypes and target them specifically, whether it be, specific types of monitoring and evaluation or specific types of interventions based on underlying mechanism. And that's part of the reason why it's so exciting to see this clustering work really come to pass, because we can start to hook into the COVID KG knowledge graph that Justin led now with those HPO phenotypic clusters that we have sort of target mechanisms to look at. So I think it's, there's still a little bit of validation work that needs to be done across the different clustering methods. And then we also need clinical review and validation from that perspective. But, I'm actually quite surprised that there hasn't been more, engagement with all of us to help, support design decisions that are being made for studies that are starting, because I think we have quite a lot of data and have made a lot of progress, as you saw today, on doing that subtyping, and it at least in its preliminary form, it seems to me would be at least worthwhile having those conversations with, more to come with the validation aspects, as I mentioned.
I think that I know, in some of the conversations we've had recently, Melissa, I couldn't agree with you more that the one of the most important things is not only identifying patients, but identifying the subtypes. So when we recruit, we know what we're recruiting for, because we finally are starting to get a definition, right? So I think that we need to start laying, how we're going to use this out in a somewhat of a one-pager, so our policy folks know how this could be used at that level. It doesn't have to be, I don't think we need to say this is ready to go yet, but if we could kind of show a roadmap where we see we need to go to use this practically, I think it would be very helpful from their point of view. How can you help me? What do I fund? That type of stuff. It would be great. And we could make you famous. We'll put your name in blinking lights. This is, your algorithm. Whatever we need, it's there. You just tell me.
I mean, I think we have tooling right now, so you can do that right now. Again, if we have tooling to get HPO terms for any patient, and we have also tooling to put them in one of these clusters. I mean, that basically no extra work is required, so it's kind of already been operationalized. I mean, there's some work to do to clinically validate what we've done and just checking things, but it's kind of.
One of the things we could, yeah, exactly. So one of the things we can do one of the things you want is sort of what is your false positive, false negative rate? So what is your positive predictive value essentially? And Melissa had a couple of great suggestions about how we might go about doing. And one might be to look at the patients who presented at long COVID centers. So that's a separate database. Obviously, we can also do this prospectively with U09.9s. But with this kind of method, we can essentially estimate a positive predictive value, or whatever you want from that kind of metric. And my question though, and I'm always a little bit critical, would be if you have a doctor seeing the patient with those items, they're probably not going to need a computer program to tell them think of long COVID. I mean, hopefully not, but.
No, it wouldn't be for that doctor. What it really is for is preparation to research, where we're saying, hey, funder, NIH, we think we can find these people, and using our honest broker, we can get in contact with them through someone indirect method, a de-identified method, and you're going to put together studies, and you're going to pay for them, right? Prospective studies, So it's really for that almost
So-
helping recruit, finding those people to
I
recruit.
understand. Oh, yeah. Okay. So, I mean, I think that the possible advantage compared to a machine learning method is that I think we can give you basically a positive predictive value. I think that's a little bit harder with some kinds of machine learning, but we probably have to test that out. But yeah, definitely we could.
I
It
think it'd be
wouldn't
very
take much
good.
more to do this now.
Thank you. And wonderful work always, as always. Guys.
That's very, 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 very exciting. And yeah, I mean, you'd be able to get a lot of nuance in the sense that if you look at the look behind pre-COVID,
Right.
what phenotype, how it evolves. And so you could probably be quite specific.
I mean, we're kind of working this up right now, but one of the super interesting things, if you forgive me for using the word super, but for instance, there's now a paper in Lancet recently that documents using VA data that people with COVID have an increased risk of diabetes, and new onset diabetes or a requirement for anti-hyperglycemic medication. And if we look at our clusters, there's a very different. I don't know if it's incidence. I don't think we can actually really say incidence with a good conscience, but we have sort of diabetes pre, during, and after, and so that we could start to not only say if somebody has COVID, but we could also say what type of long COVID do we think you have, and some of this actually might have some clinical implications, and I think that's going to require future work. So right now it's still super preliminary, but
Well, something is very interesting. So it seems a paper that I've been involved in to a degree that's coming out, or at least it's being submitted, or maybe it's been submitted. I mean, but basically it's a negative finding, and that hemoglobin A1C some period after, I forget what it is, N months after, seemed unaffected. Of course, it used propensity matching, and you could quibble with that, but I mean, it was a very interesting negative finding paper, because you'd sort of think that there'd be an impact, and maybe there is, maybe there isn't. So it would actually be very interesting. One of the things that sort of cool is when these things build on each other. So if you were to take the cohort that was built from the from this population along with the propensity match controls, and then run your clustering on it, that would be really interesting, actually.
yeah, I mean, I think it's hard to, since we're not sort of actually focusing on a treatment yet, what we haven't done propensity matching on this cohort. So this is sort of an all-comers cohort. If we were looking at sort of specific things, it becomes an interesting question of how to, because there's just so many possible confounders. But
Oh,
yeah,
absolutely. Oh, it's a complete nightmare. But it's interesting because you've got a negative finding, where normally, when people do propensity matching and they kind of want to get a sort of result, and it's like, yeah, I got my result. But this was and it was propensity matching, not on the treatment. It was basically, did you have a positive COVID test or not, with the attempts to match controls. And so this was a sort of a case control sort of thing. And I'm no statistician, so I'm not going to defend the specific method, but it seems like a really good group. But in any event, but obviously a negative result is a lack of a positive result, which is interesting. But certainly the more we can look at it and see whether, this from a bunch of different points of view, and say, okay, can you find something? So anyway, really cool stuff. Okay, and anything else? Well, this is really enjoyable, and we give people 14 minutes back, and have a great week. Thanks.
Bye.
Bye-bye.
Hi, everyone. Thank you.
Peter,
Yep.
this is Andrew.
Hi, Andrew.
I'll just follow up with you via email about something.
Okay.
A little time sensitive. Thanks.
Hey, Brendan.